So how can we quantitatively compare layer 1 security? The question is, we have these different blockchains, Bitcoin, Ethereum, Litecoin, Dogecoin, and they all are working basically on a proof of work mechanism, right? This is proof of work. And how do they compare? Like, which one is better? Which one is faster in terms of transaction confirmations? When can you accept a transaction first by looking at these different blockchains? So there are two parameters that are common to these blockchains, which is the block generation time. So how long does it take for a block to be generated, and the block size. So in megabytes, what's the size? How many transactions can you fit into a block? And if you look at the block generation time, you have 10 minutes in Bitcoin, about 12 to 15 seconds in Ethereum, 2.5 minutes in Litecoin, 1 minute in Dogecoin. And the question is, if we do have faster block generation, do we also get faster payments? And if we do have a bigger block size, do we get more throughput? But we also get slower propagation. So there might be, the dynamic is not so clear, right? So we can't like just say out of the box, this one is better because this one is faster. And in order to fully understand this problem, we have to go back and understand how blocks and transactions are propagated in a distributed ledgers network. So if the leftmost miner here finds the block B1, then it's propagating through the network. And at some point, another miner might find another competing block, the one here in red. And this means that there will be kind of a partition in the network. So these nodes will be isolating themselves because they will be looking at different realities, right? B1, the block B1 and the block B1 prime, they don't represent the same truth on the blockchain layer. Now, eventually one of these blocks will have to die or become a stale block, and that's a lost effort because the peers here, they could have worked together, right? I mean, if two people are fighting, a third person will become happy. So it's kind of like it's really a trouble here if the network is not agreeing with each other right away because they spend energy on arguing about what is true. So an adversary will have an easier game the higher the stable block rate is. And if you look at current blockchains, so we have Bitcoin, Litecoin, Dogecoin, Ethereum, these are roughly their stable block rates. And sometimes it's much lower in Bitcoin, in Ethereum as well. It's maybe fluctuates between 5 to 7%. But these are roughly the stable block rates today in today's blockchains. So if we look at security versus scalability, there is kind of like a qualitative tension that we can quite quickly observe. So the bigger the block sizes are, the slower the propagation is, and the higher the stable block rate becomes, and that's why we get less security. On the block generation time, the faster the blocks are generated, the faster payments we get, but the more conflicts arise on the peer-to-peer layer, so the higher the stable block rate gets, so the smaller the security that we get from this particular blockchain. So we have to wait for more block confirmations or for a transaction to be confirmed in a blockchain. On the other side, we have if we perform a slower block generation, we have slower payments and we get a better security, but well, it's not as fast any longer, right? So it's a drawback. And if we decrease the block size, we get faster propagation, the stable block rate decreases, and we get better security, but again, we have less throughput for this particular blockchain. So I think this dynamic is quite well understood, and this is qualitative, so we can't put any numbers on comparing objectively different blockchains. So in order to really quantitatively compare blockchains, we can, for example, use such a framework here. So we have a proof of work blockchain that's initialized with some network and consensus parameters. Like you can think of Bitcoin, Ethereum, Litecoin, Dogecoin, or any simulated network, right? You can use a blockchain simulator in order to simulate these different consensus and network layer parameters such as block size, mining power, and so on. Now, the outcome of this proof of work blockchain is a stable block rate. Right, this is kind of the characteristic of all these parameters. It condenses, it like compresses all this knowledge into this one metric. And here we can use a Markov decision process, which we will look into in another lecture. It's basically a process by which you can parameterize an attacker. And this attacker might do, for example, a double spending attack. And this attacker is parameterized with this hashing power and network propagation capabilities. So what is a double spending again? So let's recall quickly. So in double spending, an adversary performs a legitimate transaction and a double spend transaction. He sends the legitimate transaction to a vendor. He sends the double spend transaction to the peer-to-peer blockchain network. Those two transactions are conflicting. They spend the same coin. So they cannot be mined both at the same time. So if the vendor basically immediately accepts the legitimate transaction and he delivers the goods or the service because he accepts the payment, then it can happen that in the end, the majority of the mining network will accept the double spend transaction and the legitimate transaction is invalidated. That's, in a nutshell, double spending. All right, so this Markov decision process here now captures the stale block rate, the possible attacks, and we can throw this Markov decision process into an MDP solver that will solve us the optimal adversary strategies. And this is great because we can actually quantify what is the best possible adversary, right? And only once you know, this is in general, only once you know the strongest possible adversary, you can actually quantify security.